So today we are honored that we have Professor Dieter Suter for the QSI seminar series. Dieter is an experimental physicist at the Technical University of Dortmund. He has a significant contribution in promoting quantum information field in terms of papers and books. Some of his research interests are spectroscopy, scalability of quantum information processors, optimal implementation of quantum algorithms, and prolonged preservation of quantum information. Today, he's going to talk about efficient control and protection. And if you have questions, please unmute yourself during the talk or afterward. And that's starting. Please, Peter.
Okay, thanks, Clara. It was nice to have this intercontinental seminar. And since I assume that not everybody in Sydney knows where Dortmund is, I have here a map of Europe where you can see Germany. I know some people know it very well, but maybe not everybody. And you see that Dortmund is, say, in the west of Germany. And we have, as you know, a university. This is an aerial view of the campus. The highest building is the Math Tower. And the university has about 35,000 students. It's a relatively young university, certainly by European standards. It just got, I think, it was established 1970, so it was just 50 years old. So, yeah, there are other things in Dortmund for which the city is better known, at least outside of academia. And that's this symbol here, BVB09, which stands for Borussia, Ballspielverein Borussia 09. And that's the most popular soccer club here and one of the most popular of Europe. So that's, of course, also currently, say, under lockdown conditions they are playing, but they're playing without spectators. So the stadium, which has normally about more than 90,000 people in the stadium, is now completely empty. By the way, can you hear the sound from the computer? Okay, it's not important, I just was wondering. So let me start with the people who did most of the work I'm going to discuss. There's Jingfu Zhang, he's a postdoc from China. Then there's Koti Rama Koteswara Rao, in short just Koti. He was a postdoc from India, he's back in India now. And there's Swati Hepte, who's also a postdoc from India. So what are we talking about? Obviously, it was about quantum information. And in particular, what we are trying to do is to implement some kind of quantum information processing following the paradigm of the network model. So what we have normally is some kind of quantum register, which should have as many qubits as possible. And the processing starts with an initialization of this quantum register, often into the ground state. And then we apply a sequence of unitary operations, which are logical operations implemented by simple gates on individuals or pairs of qubits. And at the end, we have to read out the result of the computation. Now, that's the basic scheme, and what it requires, apart from the qubits, which should have long decoherent times, is of course selective addressing. So we have to be able to apply the gates specifically to the individual qubits. That's the basic principle with which you certainly are all very familiar. And the system we are using for that is here introduced by Marilyn Monroe. Yes, so diamonds are a girl's best friend, but you don't have to be a girl to enjoy them. And as you know, diamond consists of an array of carbon atoms which are coordinated in tetrahedral symmetry. Now, obviously, we don't use the really pure diamond, the flawless diamond. What we are interested in are specific defects inside the diamond. And mostly we use the nitrogen-vacancy center, where 2 carbon atoms are missing. One of them is replaced by a nitrogen atom, and adjacent to it is a vacancy. And these defects are the properties which actually make diamonds interesting and valuable, of course, for gems, but also for information processing. Now, this NV center has in principle 5 electrons, 1 from the lone pair of the 2 from the lone pair of the nitrogen, and 3 from the dangling bonds of the adjacent carbons. And together they have a spin 1/2. Now, this is not the state of the NV center with which we work. We actually use the NV minus, which has an additional electron, and the total spin of that state is 1. So to work with that, we use a green laser, which is reflected from a dichroic mirror and focused into the diamond by a microscope objective. Then we collect the fluorescence, which is emitted by the center, focus it onto a pinhole, and behind the pinhole we have a detector which counts single photons. This is a so-called confocal microscope setup, and when we scan this, the focus of the laser beam over the sample, we get typically images like this here. This is an area of about 10 by 10 micrometer. Inside a typical crystal, you see a number of bright spots, and each of these spots are single centers. So we choose one of these centers, and that's the one with which we work then. So we have one NV center, and the electronic structure is shown here. We have a ground state, which is a triplet A2 state, and above it we have the excited triplet E state. They are about 2 electron volts apart. Now, the triplet state is actually split in the absence of a magnetic field by the zero field interaction. The lower state is the MS equals 0 state, and the plus and minus 1 states are degenerate above it. That's for the ground and for the excited state. Now, the green laser actually pumps this system from the ground state to above the excited state. This transition is normally independent of the spin, so it's spin conserving, and that means when you excite it from the ground state to the excited state, it drops back and it then ends up where it started. That's the normal operation. However, apart from the triplet, the center also has 2 singlet states, and through a process called intersystem crossing, sometimes the excited state goes over into the singlet state. And that means, of course, it forgets its original spin state. And it turns out that from the lower singlet state, it goes back to the triplet ground state with a higher probability to end up in the MS equals 0 state than in the plus and minus 1 state. So that's a typical cycle. And it has very important consequences for information processing. One is because it ends up preferentially in the MS equals 0 state, that's a way to initialize the system into the ground state. The second, if it goes over to the singlet state, that means it takes longer and it does not emit a photon. So during this process, we have reduced interaction with the, or we have a reduced number of photons emitted from the center, and we can use that to measure the spin state. Why? Well, if it's in the MS equals 0 state, it mostly cycles just through the triplet system and emits many photons. If it starts in the MS equal plus and minus 1 state, it has a higher probability to go through the singlet state, and so the number of photons emitted is reduced. And this is a detection system that we use. The experimental apparatus looks roughly like this. We have in the center here the sample. So the diamond sits in this waveguide, and the waveguide is placed in a magnetic field. We can rotate the magnetic field around two different axes, and so we can apply arbitrary magnetic fields to the sample. And then we have this wire across the crystal, which allows us to apply microwave and radio frequency fields. So again, this was the scheme for the network model that we're trying to implement. And excuse me, I just showed you how we define our qubits. These are the nitrogen vacancy centers. And I also showed you how we initialize the nitrogen vacancy center by a laser pulse to the MS equals 0 state, and how we can count photons to read out the result. So most of the steps for a universal quantum processor are already in place. What is left is that we need the universal set of gates, like single qubits gates and CNOTs. So how do we do that? Well, let's first look at the electron spin. So we only have a three-level system, and if we apply a magnetic field, the two MS equal plus and minus 1 states are actually split, and we can address the individual transitions independently. And if we choose one of these transitions, we have our electron spin qubit, either the 0 to +1 or the 0 to -1 transition. And if we apply a resonant microwave pulse to this transition, then we can create gate operations that's best visualized by putting the state of this two-level system on a Bloch sphere. So you have the 0 state on the North Pole, the 1 state on the South Pole. Then the microwave field corresponds to rotation around this red axis. And you can orient the red axis by choosing the frequency, the amplitude, and the phase of the microwave. And you can adjust the rotation angle through the amplitude and the duration of the microwave pulse. So that in general allows you to apply arbitrary single qubit rotations on the electron spin. Now let's put that together with the initialization. As I said, this is done by applying a laser pulse, and then we have a microwave pulse which does the gate operation, and we have the readout at the end. So I'll show you one example here. We count photons, that's the readout of the final state, and then we apply a microwave pulse, and you see as a function of the duration of the microwave pulse, we observe Rabi oscillations which show that we rotate the spin around this specific axis. And this gives you pretty high fidelity actually. Here I show a longer trace of the same type of experiment, and we have roughly 100 rotations during the duration of the laser pulse. So the fidelity of a single qubit gate operation, say a Hadamard or a NOT gate, is on the order of 99%. So that works pretty well. And we can, of course, also do a free precession experiment. So instead of applying a variable pulse duration, we apply a short pulse, pi/2 pulse. We then have a delay, time t, and we measure the component of the precessing magnetization at the end of the pulse. The signal that we observe is shown at the bottom. So that's obviously not as simple as we would expect from a single qubit, where this should be a simple sinusoidal oscillation. Here we have oscillations, we also have a decay of course, but we also have some beat signals. So to understand what's happening here, it is convenient to do a Fourier transform of this signal, and we get a spectrum which apparently consists of 6 lines. And the reason we don't have we have 6 lines and not a single line is that we have also nuclear spins. And in this case, we actually have 2 types of nuclear spin. There's the nitrogen-14, which is always present in the NV center, unless you have a nitrogen-15, which you have to implant on purpose. But in natural abundance, it's a nitrogen-14. Nitrogen-14 is a spin 1, so it has 3 possible nuclear spin states, and therefore the electron spin spectrum splits into 3 equidistant lines, which are separated by a bit more than 2 megahertz. In addition, we often have a carbon-13. This is a natural abundance crystal, so you have a 1.1% chance that any of the carbons in the vicinity of the center is actually carbon-13, which has a spin 1/2. The other 99% are carbon-12, which have no nuclear spin, so they don't show. In this case, the carbon-13 has a hyperfine interaction of about 400 kilohertz, which causes the additional splitting. So obviously, we don't have just the electron spin, we also have nuclear spins, and these nuclear spins can be used as qubits. In this case, we have 2 nuclear spins. In some cases, we have more. That depends on the center, just how many of the neighboring nuclei are carbon-13. I show you here one example. Again, it's a single center. We're measuring the ESR spectrum, and you see quite a number of lines. And you can understand that spectrum if you assume that you have 1 carbon which has a hyperfine interaction of about 8 megahertz, a second carbon which has 5.8 megahertz hyperfine interaction. Then you have always the nitrogen-14, which is around 2 megahertz hyperfine coupling. And here you have a third carbon-13 with 0.4 megahertz. So obviously you have quite a number of nuclei, and you can have quite a number of qubits if you want. So we have the qubits. Question is, how do we control them? So let's go to a typical 2-qubit system. In this case, I'm looking at the 2-qubit system, which is made up of a nitrogen-14 and the electron spin. But in each case, for simplicity, I only use 2 of the energy levels. So we have a 2-qubit system and not a Qubit system. So the first step is the initialization. I mentioned that you can initialize the electron spin by a laser pulse. Now this initialization puts the electron in the ground state, and this can be ideally fully polarized. However, this initialization is not sensitive to the nuclear spin, so the nuclear spin is fully depolarized in this case. So what do we do if we want to polarize also the nuclear spin or initialize it? Well, one way to do that is you apply in addition a microwave pulse selectively to one of the 2 EPR transitions. And then you apply also a radio frequency pulse. And what you have done now is more or less a kind of swap operation. The result is that the nuclear spin is now fully polarized, but the electron spin is fully depolarized. I mean, both electron spin states have the same population. So we have transferred the polarization from the electron spin to the nuclear spin. And if you want to polarize both, we have to apply a second laser pulse, and then we have a fully polarized system. At least that's how we would like it to do. And I show you now what happens if you really do that. That's again the procedure. We first polarize the electron spin, then we do the swap, and then we repolarize the electron spin. And now I show you what happens during this second depolarization of the electron spin. We look at the population of the electron spin in the ground state as a function of the duration of the second laser pulse. So initially, we have an equal polarization. Here I show all three levels. So we have now two Qubits, and that means the target state has a population of 1/3, and we would like to bring that to 1 by applying a laser pulse. So what we would like to have is that the population goes from 1/3 up to 1 during the laser pulse. When we do the experiment, it initially starts out the way we would like to have it, but then it goes back down again to about 1/3. Question is, what's happening here? Well, the problem is that the laser pulse also depolarizes the nuclear spin. I said initially, the laser pulse doesn't care about the nuclear spin, and that's the ideal situation which we would like to have, or which we believed would be the case. It turns out it's not the case, and the curve fits quite well a model where you assume that it also depolarizes the nuclear spin with this rate Ki. And we can verify that by measuring also the other populations, and they also rise from 0. They're initially 0, they rise up to about 1/3. So why is that the case? Well, we see actually we can get the maximum polarization of about 75%, but only for, well, we cannot get 100%, and we only get that for short laser pulses. So what happens? Well, the main problem is an indirect one where the change of the electron spin changes also the nuclear spin. And that happens in two different ways in this process. One is the intersystem crossing. I mentioned that the NV- changes from triplet state to the singlet state. That changes the hyperfine interaction, and that has an effect on the nuclear spin. There's a second effect, that's the ionization. So if we change, but the mechanism is very similar, if we change the electronic structure, we modulate the hyperfine interaction, and that depolarizes the nuclear spin. So what's this ionization process? I mentioned we worked with the NV-, and that's the level scheme of the NV- between the valence band and the conduction band of the diamond. What we do with the green laser is that we excite it from the ground to the excited state of the NV-, but we also have secondary effect that the center gets ionized, so it puts one of the electrons into the conduction band, and that means the system goes over to the NV0 state, which has a slightly different energy level scheme, of course, a different spin and different hyperfine interaction. That is an important depolarization process. Now the green laser actually brings the same system back also. It reionizes the NV0 back to NV-. And that is in principle unwanted in this situation, because it makes the depolarized NVs observable again. So what we decided to try is to use, instead of a green laser, an orange laser. The orange laser also ionizes the NV-, brings it over into NV0, and therefore depolarizes the nuclear spin. However, the orange laser does not bring it back, and so we don't see those centers anymore. And if we try that, it turns out we can get higher nuclear spin polarization. You see here the red curve and the red circles. They have a higher nuclear spin polarization than with the green laser, which is the curve below. So we can somewhat optimize the process by choosing the correct photons. Another way of optimizing the process is to iterate it. So after the first polarization, we can again transfer polarization from electron to the nucleus, polarize the electron and so on. And it turns out in the case of the orange laser, we get an optimum close to 90% if we use the orange laser. So that was the initialization process. And I would like to switch over now to the gate operation. So we want to do control operations. And for this, I have to discuss a little bit the special properties of such hybrid systems. Hybrid in the sense that we have different types of qubits, in our case, electron spins and nuclear spins. And both have their advantages and disadvantages. In particular, the electron spin has a high coupling strength. It has a large gyromagnetic ratio compared to the nuclear spin. And also it's absolutely essential in this type of system because we only can use the electron for initialization and readout. We cannot directly read out the nuclear spin and we cannot directly initialize it. The nuclear spin has the advantage that it has a very long dephasing time, and of course it's present in large numbers, so we can have many more nuclear spin qubits than electron spin qubits. So let's see what we can do with that. I start here with a specific example. We have a system with a nuclear spin of 1, so that's nitrogen-14, and I only consider a single electron spin qubit, so 2 states of the electron spin, 0 and -1. And we have initialized the electron spin, but not the nuclear spin. You have the populations that you see on the left. And if we apply, if we read out the state by generating a free induction decay, we get the spectrum shown on the right, where we have three resonance lines with the same amplitude. So now we can apply controlled 2 qubit, or in this case, it's a Qubit-Qutrit operation, where we, for instance, invert the state of the electron depending or conditioned on the state of the nuclear spin. So we invert it if the nuclear spin is in the plus and -1 state. And we can read that out by, so this inversion is done by a selective microwave pulse. And if we read out the resulting state, we see that the outer 2 resonance lines have been inverted. That's the proof that we have applied this Qubit-Qutrit gate operation. Or we can do the opposite. We can invert the electron spin on the condition that the nuclear spin is in the Mi = 0 state. And we get the opposite spectrum. So this would be a controlled operation where the target qubit is the electron and the target, actually I said, and the control Qutrit, I should say, in this case, is the nucleus. Now, what about the opposite? We want to apply gate operations on nuclear spin, either single qubit or controlled qubit operations. And the 2 relevant nuclei are carbon 13 and nitrogen-14. The typical way to do that is you apply a resonant radio frequency field, either resonant with a nitrogen-14 transition or with a carbon-13 transition. And you can, of course, generate arbitrary gate operations in this way. Now, there are a few challenges to the controllability. There is the issue of addressing it, there is the issue of precision, and the duration of these gate operations, which can be quite long. Now, let me briefly discuss the Hamiltonian that is relevant for this system. Specifically for the case of the nitrogen-14, we have a quadrupole operator. We have, of course, the Zeeman operator, and we have a hyperfine interaction between the nitrogen-14 and the electron spin. Now, since it's a spin 1, we have 3 energy levels, which have this specific sequence if the electron is in the Ms = 0 state. if the electron is in the -1 or +1 state, the sequence of energy level changes as well as the separation between them. Now, this is a bit complicated, but it's also good because it means that we can identify the gate operations that we want to generate by applying suitable resonance frequencies. So this is a spectrum of the nitrogen-14. You see that we have a total of 8 different transitions, 6 larger ones and 2 smaller ones, which are so-called forbidden transitions. And we can actually generate gate operations by applying resonant radio frequency fields, as you see here. I show 3 examples where we hit 3 of the different transitions. So that works in principle. We have universal control of the system, but there is a but. And the main point is, if you look at the duration of these gate operations, they take several, well, tens to hundreds of microseconds. And that is a real problem. Why? Well, look again at this hybrid system. I mean, we have Rabi frequencies on the electron, which are on the order of 10 megahertz. For the nuclear spin, it's typically on the order of kilohertz or tens of kilohertz. And the reason is that the interaction strength, that means the gyromagnetic ratio, differs by about 3 orders of magnitude. So the gate operations on the nuclear spin become quite slow, and the dephasing times are quite different. The dephasing time of the electron spin is typically on the order of some microseconds. The dephasing time of the nuclear spin can be several tens of milliseconds. And why is that a problem? Let me give you a specific example. We look at the 2-qubit gate. We start with the excitation by the laser, which initializes the electron. Then we apply a microwave pulse, which is a single qubit gate operation or a controlled gate operation on the electron spin. For detection, we apply another microwave pulse and a laser pulse and count photons. Now, if we only do that for the electron, that's fine. But now let's assume we want to apply nuclear spin gate operation. So we apply a radio frequency pulse, which is typically much longer than the pulse on the electron spin. This is not to scale. So it's actually, in reality, it's even much longer. Now, what we expect under such a gate operation, say this is a controlled rotation of the nuclear spin, so we would expect a roughly sinusoidal modulation of the signal as a function of the pulse duration. That would be the ideal signal. If we do the experiment like this, I call this an unprotected gate operation, we just see a decay. And the reason is that this first microwave pulse creates a superposition state of the electron spin, and that electron spin coherence dephases during the application of the radio frequency pulse. And so we lose the coherence, we lose the quantum information, and this doesn't work in practice. Now, one way to solve this problem is that we use so-called protected gate operations. We stop the radio frequency for a moment. I'll tell you later why we stop it, and apply a dynamical decoupling pulse or pulse sequence on the electron spin, which refocuses the electron spin coherence. So we get a longer dephasing time, and we get actually almost ideal operation under this condition. So this is a protected gate which refocuses the coherence. That's one possible solution. But there's still another but, or there are more buts. And one is that I told you the interaction strength of the nuclear spin is quite weak. So to drive them, we need rather strong radio frequency fields. Now, these radio frequency fields are very far from resonance for the electron spin. And so you would expect that they don't affect the electron spin. They're really far from resonance. However, there are non-resonant side effects. And it turns out they're quite important. They shift the transition frequency of the electron spin. And I show you an experimental example here. We measure the coherence of the ESR transition by counting photons, as normally we have resonant detection. So we detect it in a frame of reference which rotates with the Larmor frequency of the electron spin. And so all we observe during the RF pulse is a decay of the signal, a slow decay. This is if the radio frequency field is off. So the pulse is only virtual, the amplitude is 0. Now we can fit that, of course, with the decay function, which is this red line. Now we apply low power pulse, which corresponds to a weak radio frequency pulse. And you see that now we start to see oscillations, and the oscillation has a frequency, in this case, of about 5.7 kilohertz. I call this mu BS. And if we double the power, it turns out this precession frequency doubles. And this precession frequency indicates that the transition frequency of the electron spin shifts, as shown in the right-hand part of this slide. And if we double the power again we double the precession frequency. And so this new BS, that's a so-called Bloch-Siegert shift, which is a second order effect of this non-resonant AC field on the electron spin. Why is that a problem? Well, it mixes up the coherence of the electron spin, so it also scrambles the quantum information, and it increases linearly with the radio frequency power that we apply. So to sum up the problems of this control approach, which I call direct control, well, the gate operation is too long. It just takes too long to implement that gate operation. Then I showed you that we have to cover quite many frequencies. I mean, in the case of N14, we have 6 or 8 transitions, as you've shown. In the case of carbon-13, this is a typical carbon-13 coupled by hyperfine interaction on the order of 100 to 150 kilohertz. These are two different elements of the hyperfine tensor, and the Larmor frequency of 158 kilohertz. So we have two different transitions depending on the electron spin state. If you want to excite such a spectrum by applying a radio frequency pulse, you would need a Rabi frequency on the order of 1 megahertz, which is just not feasible experimentally. You can never have enough radio frequency power to do that. And you would completely scramble the electron spin by the Bloch-Siegert shift. So you have this problem with the non-resonant side effects, which I just discussed. So what are the solutions? I showed you one solution. You can refocus the coherence. That solves the problem of the decoherence to some degree. And it also can refocus this Bloch-Siegert shift. So that is a pretty useful version, but there's a simpler version actually. We just don't use radio frequency fields. So since the radio frequency field causes problems, we just do away with them. Now the question is, of course, if you don't have radio frequency fields, how can you control the nuclear spin? And the idea is that we use the electron spin, or the hyperfine interaction between the electron and the nuclear spin. Now the hyperfine interaction as such alone is not suitable for controlling the nuclear spin, but the combination of the hyperfine interaction with control operations on the electron spin can do the job. And there are actually two ways to do that. One is to use Raman excitation. So it turns out, I showed you that you can have so-called forbidden transitions which change the electron as well as the nuclear spin state simultaneously. And that means you can have such lambda systems, for instance, where you can excite two adjacent transitions with single microwave field. And that allows you to apply Raman pulses to the nuclear spin transitions. Raman, not in the optical sense. So the fields that use are microwave fields, but they're Raman transitions in the sense that you use two fields to control a third transition indirectly. So that's one option. And I just show you here some experimental results which prove that this actually works. Now, there is a second option, and I don't have time to discuss both, so I spend my last few minutes on the second option. We don't apply a Raman pulse, but we apply time-dependent pulse sequence, and the result of that pulse sequence is an effective field acting on the nuclear spin and controlling it. Why do we do that? Well, for two reasons. One, the main reason is that because the hyperfine coupling is much stronger than the Rabi frequencies that we can generate, we get faster gate operations. So it reduces, for instance, the problem of dephasing of the electron spin during the experiment. The second reason is we simplify the experiment. We don't need RF pulse. We only need microwave pulses, which we need anyway. And if we don't apply radio frequencies, we don't have problems with Bloch, Siegert shift, and so on. So that solves a number of problems at the same time. How does it work? What we want to apply, for instance, a gate operation to carbon-13 is to create an effective field, and in such a way that the nuclear spin rotates around this effective field. Now, to have a specific example, I assume here that initially the carbon spin is aligned with the effective field and the electron spin is in the ms=0 state. So the effective field on the nuclear spin is given simply by the Zeeman interaction. And omega 0 is gamma times b, and the field direction is applied with the magnetic field direction. Now, if the electron spin is in different states, say the +1 state, we have, in addition to the Zeeman interaction, also a hyperfine interaction, here written as A. And this hyperfine interaction in general points in a different direction than the Zeeman interaction. So if the electron spin is in the +1 state, then the effective field points has different amplitude and different direction as shown here by the black arrow. And if we switch now the electron spin to the ms=-1 state, we flip the direction of the hyperfine field, and the new effective field, total field, which is the vector sum of omega 0 and A, points in a third direction, this new black arrow. So by flipping the electron spin, we can apply or generate effective magnetic fields on the nucleus in very different directions. And if we do that here in this example, the effective field flips away from the z-axis, and that means the nuclear spin starts to precess around this new effective field direction, and we can observe that experimentally as an oscillation in the populations. So that again is a way to achieve universal control of the nuclear spin, or actually of the combined system consisting of electron and nuclear spin. So that's how it works effectively. You have, in this case, a single qubit of the electron and a single qubit of the nuclear spin. So we have 4 logical levels. We apply a first microwave pulse, and that switches the electron from the 0 to the 1 state. And that means the effective quantization axis changes and the nuclear spin rotates around this new quantization axis. Now, this will in general not allow us, say a single such pulse will not allow us to generate an arbitrary unitary gates. Also, some useful gates can be obtained that way. So what we do, we just apply more than one pulse, for instance, in this case, 3 pulses. And so we have 3 rotations around 2 non-parallel axis, so around 2 different axes. And with this, in general, you can achieve universal control. And to get a specific operation, you just have to adjust the times between the pulses and the durations of these individual pulse sequences. So that gives you a typical control problem, and you adjust the timing and the phases of the pulses to achieve either single or 2-qubit gate operations. Just again to illustrate that, I show here the evolution here first for the electron spin during such a pulse sequence. The diamond is the initial state of the electron spin, which is initially in the logical, in the ms equals 0 state, and the red ball is the final state. So the pulse sequence here brings the electron actually back to itself, while the carbon, which is the nuclear spin, which we actually target, goes from the north pole to a point near the x-axis, and this operation actually corresponds to Hadamard gate on the nuclear spin. Or we can apply a controlled knot operation. So if the electron spin is in 0, it ends up in 0. The nuclear spin also goes from 0 to 0. While if the electron spin is initially near the south pole, so here diamond and ball are near the south pole, then the nuclear spin is actually inverted. So obviously this pulse sequence, which has different parameters than the Hadamard gate, allows us to apply a controlled knot operation. And we can combine these gate operations to do useful things. For instance, we can start with the system in the electron spin ground state. We apply then a operation U, which is in this case designed to generate nuclear spin coherence with the electron in the -1 case. And so this is an operation to generate nuclear spin coherence. We can do the inverse operation, which takes this nuclear spin coherence, converts it back into electron spin population, which we then read out with the laser pulse. And we can then, for instance, vary the delay between the two operations to observe free evolution of the nuclear spin. This is this sinusoidal evolution on top. If we do a Fourier transform of that, we observe a nuclear spin spectrum for the case that the electron is in the ms equal -1 state. And we can do the same operation for different electron spin case states, so that we observe the oscillations for the electron in ms equals 0, -1 I've shown before, and here for the case of ms equal +1. And if you do Fourier transforms of these signals, you get 3 different spectra or 3 different resonance lines, which correspond to the 3 electron spin cases. So we also have full control of the nuclear spin in this case. And the fact that it's full control or universal control can be shown if you take the drift Hamiltonian, so that's the static system Hamiltonian, which consists of the zero field splitting and the Zeeman interaction on the electron spin. Then we have the Zeeman interaction on the nuclear spin and the hyperfine interaction between them. You combine that with the control operations, which are microwave pulses on the electron spin, and then that means you can reach every possible state in this, well, 9 or 6 level system, depending on which nuclear spin you choose. And so we have, as I mentioned, a control problem. We have to vary the pulse durations, the phases, and the delays between them, and that allows us to generate the necessary operations. For instance, a Hadamard gate can be obtained with these parameters, or you can do a C0 with a different set of parameters, or a swap operation. So you swap the electron spin qubit with the nuclear spin qubit. Now you can continue. You cannot just generate single gate operations this way. You can do full quantum operations, quantum algorithms, like a Grover search operation. So this is a Grover search for 2 qubits, so pretty simple system, admittedly. But if you write it out in terms of single qubit gate operations, the conventional Hadamard, C0s, and so on, phase gate operations, you get this picture, which has quite a large number of gates. This includes here the Grover gates for the 1,1 and the 0,0 target states, and I show here on the bottom the remaining 2 possible target states. So it turns out you can implement the full quantum search with a single sequence of microwave pulses. So we only target the electron spin, but we implement the full 2-bit qubit algorithm. For instance, for the target state 1,1, we need these 4 pulses with 5 delays and for, well, 3 different phases of them. And if we do that, we measure the final state, which is mostly in the 1,1 state, as we would expect. And we can do the same for the other target states, so the 1,0, 0,1, and 0,0 states. They have the same number of pulses, but different parameters. So I guess my time is up. I would like to come to the conclusions. I don't have really to tell you that quantum computers can be very powerful and that it's not very easy to realize this potential. What I tried to show that hybrid quantum registers, in my case, they are electron and nuclear spin qubits, have a number of challenges and opportunities, and that indirect control can sometimes be very helpful, that you can simplify the experiment and you can get rid of some problems like Bloch-Seeger shift. And I would like to thank you for your attention. And if you have any question, I will be happy to try to answer them.
Yes, if anyone have question, please ask. So I would just ask about the scalability of quantum networks out of MV center qubits. I don't know if this mechanism helps actually when you have you put many MV centers in an area, and certainly you have better control or better control methods, and how this helps actually.
Well, I would say in terms of controllability, I see no fundamental problem. Of course, it will be more challenging if you have more qubits, but it should still be possible. Now, the main problem from my perspective is how to create controlled arrays of NV centers. And this is not something I can do. I know many people are trying to do that, for instance, by implanting single centers with high resolution, but so far the progress in that direction has been quite slow. And I'm not sure if diamond is the ideal. There are other options like silicon carbide, where you have similar centers, so control operations would be similar, but maybe they are technologically more suitable than diamond.
Thank you. If there's any other question, please ask.
Thank you, Dieter. So it's motivating to see that indirect control actually has some practical application. I always worried that it might be too useless, but I mean, there's a kind of no free lunch theorem in some sense, right? I mean, there is some cost in doing it indirectly, and I guess that's mostly time cost. Or what would you say are the disadvantages of doing it this way?
Well, in the case of hybrid system, the time cost is actually negative. I mean, definitely these operations are significantly faster than the direct control.
Because your couplings are strong enough.
Exactly, because the hyperfine, well, I mean, depends which system you choose. Say in the case of N14, the hyperfine is 2 megahertz. In the case of carbon, it goes from 0 to 100 megahertz. The ones that we work with are on the order of 100 to 300 kilohertz. And the corresponding Rabi frequencies are at least an order of magnitude lower. Actually, in some cases, we've never been able to even see direct control of the carbon.
Right. Okay. Interesting. I guess one problem is if you want to. Oh, sorry. Go ahead.
I showed you these oscillations on the N14. There, the gate operation was hundreds of microseconds. Now, these indirect control operations, the whole sequence typically is on the order of 10 microseconds.
Right. Okay. Thank you.
So if there's no other question, I thank you, Dieter, on behalf of everyone. Thank you.
You're welcome.